How's it going, YouTube? It's time for another topic review. If you're new to the channel, new to the playlist, my name is Seth Abney, and I am a student currently at the coding boot camp called the Flatiron School, and I'm enrolled in their data science program. There's 5 phases in the boot camp. I am currently on the tail end of phase 3, and for this phase, as a matter of just enriching my study process and retaining a little bit more of what I learned, I'm doing the study vlog where I review what I learned at the end of every module. In phase 3 there's like 11, 10, 12 modules, something like that. I just finished the very last module of the phase. So after this module, the next step for me is to come up with what my milestone project will be and submit a proposal for that. I'm not going to share any more details about that right now because I'll probably make a video about it after this one directly. So, Module 31, let's get into it. And before we do, again, disclaimer, I'm not doing this on behalf of Flatiron. This is purely for my own enrichment and your entertainment. There's a little bit of, sometimes I use code snippets. I don't think I have any code snippets in this notebook, but there's some like images and things like that that are from the curriculum at Flatiron. All credit goes to them. If you want to check out Flatiron, what it can offer you, that link will be in the description below, as well as my GitHub and my LinkedIn and all that good stuff. So now let's get into the notebook. So we're in Module 31. Today we're going to talk about ensemble modeling methods. I'll explain what that is here in just a moment, and some particular types of ensemble models. You see them titled right here: random forest, adaptive boosting, gradient boosting, and so on. So before we talk about the particular models, let's talk a little bit about what ensemble methods are. So ensemble modeling is a strategy that involves using multiple models at the same time to come up with a better prediction than what a single model would on its own. So if you see this visualization right here with these targets, this really, for me, demonstrates really well what, can I zoom in VS Code? Oh, I can, okay. So this really like visualizes for me like basically what's going on with ensemble models. So you might have one model that's highly precise or highly accurate, which is what's represented by this target on the left here. This is kind of an ideal situation, and it's not. This is like a 90% something accuracy or precision or whatever like this model represents. So that's not probably realistic to expect this level of precision out of a single model. Potentially, if you had big enough data and a robust enough pre-processing and hyperparameter tuning workflow. But nonetheless, ensemble models generally tend to perform better than single models on their own, like almost across the board, especially like in the competition sort of scene. So what a ensemble method utilizes is the idea of the wisdom of the crowd. And where this concept, the wisdom of the crowd, came from was some professor at some school way back when. He had a bunch of students guess how many jelly beans are in this jar that he put in front of the class. And what he ended up finding was when he averaged the predictions of all the students, that number, the average of all the predictions, was actually closer to the true number than all but one of the students' individual predictions were. So ensemble methods kind of in that vein uses multiple models to make multiple predictions, and it sort of uses the aggregation of all those predictions to make the prediction of the ensemble model. So you can imagine that if we took all these data points here and this target on the left and we sort of averaged them, they would converge into a distribution very similar to what you see in this one I said on the left. The one on the right, it would converge if we averaged it to a very similar distribution of what we see in this one on the left. So you might have a model that makes like these predictions, and you might have another model that makes these predictions and these and so on. But then if you average the predictions of all those models, they'll all sort of regress towards the mean, right? So that's kind of what's going on with ensemble modeling. The disadvantage is that it's very computationally expensive between training your models and validating your models and storing those models, those objects in memory on your computer and all that. It takes a lot because you're not dealing with just one model at a time anymore. You're dealing with multiple models at the same time. So this isn't going to work if you're using like a Raspberry Pi for your daily computer, probably. Going on. Oh yeah, let's talk about bagging real quick before we get into the specifics. So there's all sorts of different ensemble models, just like there's all sorts of different models. They all sort of have their own advantages and disadvantages. They all basically utilize the same basic idea of bagging, which is an acronym, or if you will, a conjunction for this phrase bootstrap aggregation. So what bootstrap aggregation means is you're first bootstrap sampling data, which means you're sampling some amount of the data with replacement. So if I have 100 data points and I sample 50 of them, I'm putting those same 50 back. So there's still 100 data points to sample from the next time I sample. That's all bootstrap sampling really means, for the sake of this discussion. And the aggregation part is where we take we aggregate the predictions of all the models. So every model is given like a bootstrap sample, and it makes predictions based off that bootstrap sample, and then we aggregate the predictions of each of those models. So an aggregation could be a lot of different things. Like some models use a voting system, so it's just like you have 10 models and 7 of them vote one way and 3 the other. You're going to go with the prediction that the first 7 made. You might take the mathematical average, like to the mean. In other words, you might take the I was gonna say the mode, but that would just be like the voting system. If you took the most common occurrence, what's the third one? Your median. You might take like the median of all the predictions. So there's different ways of calculating, aggregating whatever that aggregation is, but the idea is that you're taking some subsample for each model. You're replacing that subsample, so some observations are going to occur in multiple models, and then you're aggregating the predictions made off of each of those subsamples. Basically, all ensemble models use bagging in some way, shape, or form. So there's a few different, like I said, types of ensemble models. First, we're going to talk about random forests. And a few episodes back, I talked about decision trees and regression trees. So if any of this isn't quite following, maybe go back and check out that video. That was module, it was 25, 26, 27, 28, somewhere around there. It'll say in the title, like decision trees or something along those lines. Matter of fact, I might link it in the description below if I remember to do that. So what a random forest basically is it's a ensemble, a group of decision trees, right? But the problem is that tree-based models are completely deterministic, meaning that if you give the same tree with the same hyperparameters, the same data, if you have two different trees with the same hyperparameters, the same data, they'll both become the exact same tree. There will be no difference between those two models. They'll, for all intents and purposes, be the same model. Which kind of defeats the whole purpose of ensembling models, right? Because the point is that we in fact want some variance between our models within our ensemble. So we do this, partially this is accomplished by using bagging. So for our random forest, we bootstrap sample our rows from our data set for each individual tree. And so we'll sample 2/3 of the available data for a given tree, and then we'll use the remaining third as your validation set. You're basically doing a 66-33 train test split on your data, but you're replacing like the training set, right? And you calculate your out of bag error, which is your error term for that particular tree. So then to create further variability, because you can imagine if you had enough trees in your ensemble, they might get the same samples or similar enough samples. So, and it's important to note, we're sampling like that 2/3. We're not sampling like in order like the 2/3. You're taking randomly the amount of 2/3 like from it, right? So that helps create a little bit of variance as well. And then we sample the subspace within each tree, which basically just means that we're randomly selecting features or columns like from that data. So we'll get 10 different trees, and we'll do our we'll bag each tree, and then once each tree has its bagged data, then we go back and we randomly select like which columns we're going to leave for that tree and which columns we're going to drop from the data in that tree. So every tree, it's almost guaranteed, is going to be different in some way in terms of the data being passed into it, right? And depending on, at least all the random forests I did in this module, this might be different, but all the random forests that I built in this module, all the trees within the random forest use the same hyperparameters. I can see like that maybe you would build a random forest where you have different hyperparameters for various trees in the forest, but I didn't do that in this module. So maybe that's a really bad idea. I don't know. But something to maybe look into if you're curious. But at least for the sake of this module, all the random forests I did, all the decision trees within the random forest that I built had the same hyperparameters. So they use the same minimum leaf split or max depth or like whatever. So this rigorous bagging and subspace sampling workflow basically makes the random forest model extremely resilient to overfitting, because like no single tree in the model has all the data available, so it's basically impossible to overfit data that you don't actually have, right? But again, that comes at the cost of computational complexity. It takes a lot of RAM to build the model in the first place, and then you have to sort of keep that RAM occupied as long as that model is existing on your computer and you're using it. Until, of course, if you decide it's a good model and you want to use it again in the future, or you want to deploy it, you can pickle that model and deploy it. And if you're wondering what pickling is, you can go and look at the very previous video from this one. This is where we talk about pickle files and stuff like that. So that's a random forest. Basically, it's just a collection of decision trees, and they're all given like a randomly sampled subset of the data. It all comes from the same data source, of course, and then you aggregate the predictions of each of those trees, and then that spits out your best possible prediction in theory. So let's talk about boosting algorithms. So just like ensemble methods, there's a whole family of types of models. Within that, you have boosting algorithms, which is a whole sort of like family of models within ensemble methods. They're similarly effective to random forest, but they have some notable differences in terms of like exactly how they work and like what's going on under the hood. So one thing is that they build models iteratively. So how one model is built, so in a random forest, say you have 10 different decision trees, all those trees are being built like in parallel at the same time, and what happens in one tree is not affected at all by what happens in the other tree. The only thing that's affecting what happens in that tree is exactly which data is sampled and passed into that tree, right? So versus with boosting algorithms, that's not necessarily the case. Like exactly like which subset of the data is sampled and passed into like the current model might affect how the next model is built. And the models are built in line. They're built sort of one at a time rather than in parallel, the same way or the way like they are in random forests. The other thing is that boosting algorithms utilize weak learners. So in a random forest, every tree that you build is like, even on its own, like a pretty good decision tree, right? And you're building the algorithm wants to make that even that individual tree as strong of a learner, as good of a model on its own as it possibly can, right? And the idea is you have a confluence of really strong learners, and then you're going to have like a super strong learner, like in the as the ensemble. Boosting algorithms, however, use weak learners, and so like you're building, like when one model is being built, it might be generally really bad. However, it's really good at capturing like one particular aspect of the data. All right. So, and that's why that's part of where like the iteration comes from, is so then you iterate and you have like this ensemble set of models, and each one of them like doesn't generalize like very well, but it sort of overfits to like one particular like dimension or aspect of the data. And so then like as an ensemble, all of those models together generalize extremely well, because you're sort of taking the best aspects of each of these weak learners. So boosters aggregate differently. So random forest, they use a voting system where you basically would take the mode. So you would have 10 different trees, and they'd all give you some prediction, and you would take the mode of that set of predictions, right? So the most common value that's predicted, right, or whichever the majority rules with random forests, right? Versus boosting algorithms they weight the importance of the predictions of each. So you have 10 different models in your boosting algorithm, and different models within the ensemble are weighted to be more or less important than others. And there's different types of boosting algorithms, and so there's different ways that weighting system is like calculated, right? But nonetheless, all boosting algorithms do use this weighting system in some way. So they're not really like, it's not like you have these different models voting on it so much as you have these different models contributing to some prediction at varying degrees, or at varying degrees, right? So the two types of the two types of boosting algorithms that I went over in this module is AdaBoost and gradient boosting. So first we'll talk about AdaBoost. AdaBoost is just short for adaptive boosting. This was the first boosting algorithm that was invented, and basically it builds a model, and then when it validates that model, this is what this visualization is for, then it looks at which observations were misclassified, and then those observations that were misclassified are weighted more heavily in the next model. So you can see like we have this model 1 here, and we go to box 2, and these plus signs that were misclassified, they should have been captured in the blue area, but they weren't. They get weighted heavier in this next one, and so they end up getting properly classified. But now these negatives were misclassified, so then now you can see they're bigger and they're weighted more heavily in the next one. And then when we aggregate these various models with their various weights for the various data points, we get a pretty good capture or prediction of the observations. So you can see in box 4, there's really only one data point that was misclassified, versus the rest of them, like a majority of the data is misclassified. But as you can see, like in aggregate, it's pretty good. So this is a quote from the curriculum. I thought it was just nice. Adaptive AdaBoost creates new classifiers by continually influencing the distribution of the data sampled to train each successive learner. So they affect the distribution by assigning new weights to various parts of the data. And in addition to AdaBoost, we have gradient boosting, which is a little bit more complex than AdaBoost. So it's similar to AdaBoost, but the difference is that after validating a model, and gradient boosting also uses weak learners, instead of just weighting the misclassified data observations more heavily, it actually calculates the residual of the misclassification. So I'm going to use a little bit of language here with like residuals and error terms and stuff like that. If you're curious about all that, I don't want to spend a whole lot of time here. Go scroll back earlier on into this phase, and or maybe even go look at some of the live streams of my phase 2 project, and you'll learn a little bit about residuals and that sort of stuff there. But basically, a residual is the difference, literally like the distance, the difference between like the actual data point and the predicted data point. So it calculates the residuals of the misclassifications, and then that is passed into a loss function, which is just like a fancy calculus formula, basically. And then you calculate the overall loss of the loss. Where'd it go? The overall loss of the model, and then the overall, and then you can use the loss of the model to calculate the gradient, which again, that went over pretty heavily in, I want to say, module 23, 24, something like that. Look up, there's a whole video I did, there was a whole module over gradient descent, and that's all there. So by calculating the residuals, we can calculate the loss, and then which we can calculate the gradient with, and then we can pass in the overall loss value and the gradient as predictors when building the next model. So remember, boosting algorithms are iterative. They build one model and then the next. So we use basically the degree of error in one model as a way to we pass that information in basically as a predictor into the next model, and then that next model as it's being built kind of takes that error into consideration, and that helps make a better prediction with each successive model. And this visualization doesn't make things as clear as the AdaBoost one did, but especially if you're not familiar with regression and gradient descent and all that. But this is the visualization they provided for gradient boosting, and so you can see that, like, look at like this little shape here. You can see that these data points are sort of getting compressed with each successive tree model that's used. And also, there was like a whole lab done on this thing called XGBoost, which just means it's short for extreme gradient boosting. All XGBoost is its own library, completely separate from itself. It has implementations available in Python, C++, and a few other languages. But it is gradient boosting algorithms, a whole package, a whole library that's made like specifically for this one like particularly good gradient boost algorithm. And it's apparently become like kind of a meme that a lot of competitions on like Kaggle are won using XGBoost as opposed to any other kind of like ensemble method. So that's supposed to be like the best ensemble or boosting ensemble algorithm out there right now. I do know that the curriculum that I'm using for Flatiron is, my cohort leader told me the other day, it's like about 2 years old, which kind of makes sense because that's like about when COVID started. So I imagine they probably didn't, production across all businesses was slowed down a little bit through quarantine, and so that makes sense to me. But long story short, XGBoost is supposed to be the kind of premier or preferred boosting algorithm, gradient boosting algorithm out there. Again, it's not just a boosting algorithm because AdaBoost is different, but it's a gradient boosting algorithm. There's gradient boost model objects available in scikit-learn. XGBoost, like I said, is its own library, and you have to install it separately, and you can't pip install it. You have to conda install it. But it's fortunately the API for it is written to resemble like almost identically scikit-learn. So the way you import it and instantiate objects and fit data to it and like all that stuff is the syntax is basically identical to scikit-learn. The only difference being that you have to just import it separately than from scikit-learn. Yeah, so XGBoost is cool. So that is it for today. We talked about gradient boosting. We talked about AdaBoost, which is all different tools available within the family of boosting algorithms. We talked a little bit about random forests, which are their own sort of ensemble method. And we talked a little bit about just what ensemble methods are in general. So I hope you enjoyed this video or got something out of it or learned something. Again, if you're interested in Flatiron or curious about what it has to offer you, I will have that link available down below. You can also just Google Flatiron School pretty easily. If you want to connect with me on LinkedIn, ask me any questions directly, or just connect and engage, I'd be happy to. LinkedIn link will be in the description below, as well as if you'd like to explore this notebook or any of my other repositories on my GitHub, I'll have my GitHub link down below there as well. Yep. So with that, that is going to be, folks, the last study vlog for this phase. And I have some ideas about maybe a little bit different way of doing my study vlog for the next phase, but I'm going to keep that for a surprise later. I will, however, continue to do some videos, some vlogging within this phase, but it's going to be from here on out over the me building and working on my milestone project, not on necessarily like learning new stuff. Now I've like learned all this stuff in this phase, and now it's time to put it all into practice and like really kind of concretize it in my mind by using it, right? And I have another couple like projects on my mind that I think are just really fun, and they're this type of stuff like modeling and that sort of thing. So that might be coming up in the near future too. It kind of depends on how deep in the weeds I get with the milestone project for the phase. So yeah, like I said, hope you enjoyed it. Check out those links down below, and I will see you next time.